Good evening. Tonight I'd like to talk to you about failure mechanisms. These are processes which cause a product to break or to become less satisfactory or to become useless in some other way. And the reason I'm asking you to look at these is because you've now got to the stage where you've come up with several ideas for a prototype, and I want you to swap. So I'll be uploading a list of names so you know who to swap with, and then I want you to constructively criticize the other person's idea and say, well, these are the ways in which this prototype might fail or might be unsatisfactory. And I'd like you to take you through the main failure mechanisms tonight. Here I've got on the board, I've got what I like to think of as the big five of destruction. And I'll go through these one by one, tell you what they do to the materials, and you can think about these when you look at your partner's concept. The first one is wear. Wear is essentially the mechanical removal of the surface layer of material. So the surface layer of material gets turned into a powder or smeared into a different place. Usually when you're talking about a crumbling action where you get small neat particles broken off the surface, that would be known as abrasive wear. That's essentially what you get when you take a stick of chalk and you pull it down the blackboard. You get the powder left behind, stuck to the surface of the blackboard, and you can shake off the powder. You can see that it's still loose. It's still individual particles. If instead you take a crayon and you dragged a crayon down the blackboard, you wouldn't be able to scrape it off because that's then stuck to the surface, it's smeared on. That's what you would think of as adhesive wear. Now, here I've got some examples. This is a brake disc from a van, and you can see here the surface here where the composite brake pads have been touching it is polished to a clean silvery color, and that's the bare steel. And over time, over the course of a few years or a few 100,000 kilometers, this will get too thin. I believe it says on here what the minimum thickness is. Yes, it says here 8.4, presumably 8.4 millimeters, and then this will need to be swapped for another brake disc in case it gets too thin and breaks apart. The other kind of things that can be affected by wear. Here's a very old small wood cutting axe, and you can see here the cutting edge is no longer so sharp, and this is because it's got it's been worn, some's come off, some's got deformed, that sort of thing, and then now and then you'll need to take it to a grindstone and sharpen it to restore the cutting edge. The second mechanism I'd like to talk about is corrosion. Everyone knows corrosion is the thing that makes orange rust and makes holes in old cars and that kind of thing. And essentially what happens is when you create the metal in the first place, you take some ore. This is a piece of magnetite, so iron ore, and then you heat it up because it takes a lot of energy that needs to be put into the materials to make the chemical reaction go in the direction of turning an oxide like this or a sulfide into a pure metal. So you have your pure metal, and then when it gets hot or wet, then it has a tendency, because energy is then released by the reaction going in the opposite direction and creating an oxide, it has a tendency to create this oxide. And most of the oxides are much, much weaker than the pure metals. Here you see this piece of magnetite. You wouldn't be able to make a thin component out of it that was a millimeter thick or something like that. It would be so brittle as to be useless. Here's an example of something that's been degraded by corrosion. This galvanized bin here. Now, this bin has probably had some fallen leaves sitting in the bottom of it, maintaining some dampness in the bottom. And then you've had wet corrosion So an electrochemical process, then slowly eating away the iron at the bottom and turning it into iron oxide, which is then weaker. Probably then it's been loaded by putting stones or wood or something in it, and eventually it's split open. And you can see here, it's because the bottom's got so thin, it then hasn't been able to support the load, and it's left the bucket looking very sad. Some people might ask why this has happened, when you can see that the sides of the bin here are still galvanized, so they're still covered with zinc, and the zinc is more reactive than the iron, so it ought to corrode in preference to the iron and protect the iron. The answer is presumably that only the bottom of the bucket where the zinc layer, probably through mechanical wear, has been damaged, has been kept wet. And that means that the electrons which have been taking part in the corrosion process haven't been able to flow up the sides here and corrode the zinc. So corrosion can make things much weaker. Basically, it's a loss of strong material, which is then replaced by weak material, and the weak material then flakes off, and then often your part will then split open or bend or fail, that kind of thing. But it can also do things like expand. So here's a pair of calipers, which are either made out of regular tool steel instead of stainless steel, or they've been left in corrosive environment, and you can no longer open them, or you can barely open them, and because the rust has expanded, because the iron oxide has a larger volume than the iron. Other things it could do, iron oxides are usually very bad electrical conductors and thermal conductors. So here you can see a soldering iron, and this is a big hammer type soldering iron of about 300 watts. And you'll see on the end here, this is actually not very good for soldering anymore because the copper has become corroded. You may find that the connections where the wires are then screwed onto the heating element might also become corroded, and you might find they will then stop working. They'll stop allowing current to pass. You'll find that's more often a problem with low voltage equipment, because there isn't much of a spark to jump across the oxide layer and burn through it, and everything needs to have a very low resistance for it to work. So you'll find with things like a welding set, sometimes the earth clamp, if it gets corroded, will no longer work, or in a vehicle, if the battery post terminals get corroded, especially if it's an old vehicle with a 6-volt electrical system. So not only are corrosion products, things like rust, weak, they're also larger than the iron, so they can break things open and they can cause things to seize. You see that on some bridges. And they're also poor electrical conductors and poor thermal conductors. So there are plenty of ways that they can cause things to break and fail. The next failure mechanism I'll look at is fatigue. Now, fatigue means that a component is subject to a cyclic load, and this cyclic load, in the worst case, goes right the way through zero. So you've got half a positive cycle, half a negative cycle of stress, and over time, if these peaks and troughs are large enough, then they can cause cracks to form and grow. And with some materials, there's a limit below which this won't happen, the fatigue limit or endurance limit, and with other materials under a cyclic load, it will always happen over time. But the fatigue limit is usually something that's below the elastic limit for the material, so something you need to be careful of. Here, this is a bush from an excavator, and you can see here that it's presumably been placed in bending somewhat in the center, because there's a slight groove so that the grease can get around it, and over time it's cracked from this greasing hole around the edge there. This would be something that would be under quite a high load in operation, probably something like 11 tons force, if I remember rightly. Another common place you'll see fatigue is where you have flexible cables. Here you can see some headphones, and these have failed here because the connecting cable has been bent back and forth so many times that the cores have broken and left an open circuit. The fourth mechanism I'll mention is creep. Now, creep means that you have a load on a component and gradually, over a very long time, it changes shape. Closely related to creep, you have relaxation, which means that you have a deformed component held in a certain geometry, and over time the stress relaxes, so you have less stress in the material, and that then becomes the default shape of the material. Creep is something that you'll often see if you have, say, a bookcase, and the bookcase is too heavily loaded. You put too many books on it, and then it starts to sag, and then when you take the books off after a year or two, then the shelf remains in a bowed shape. It doesn't spring back again. I couldn't bring a bookshelf along today, but I could bring an example of relaxation. This here is a car fan belt, and you can see here it's folded up in this package here, even though in its default state it would be a circle. And if I take it out of the package, it stays more or less in that shape because the material has relaxed and taken up the new shape. In this case, it wouldn't be harmful. The last of the big five is sudden damage. Now, this means that some component gets broken, from one moment to the next. It's not something like fatigue or corrosion that takes months or years or decades. It's a sort of bang thing that happens. And it's often the end result of one of the other processes, like perhaps wear or corrosion. A loss of material then causes something to break. And it can happen in three ways. You can get a brittle fracture. Like here you can see this pretty glass dish. It's been dropped and a piece is just broken out of the rim. You can see there's been no deformation of the material, it's just broken off. You can see a similar thing here with this part of a car wheel disc. Again, a brittle fracture. And this is probably something like ABS or some polymer blend. I don't know which one, but something which is quite brittle, and when it's hit a curve, it's shattered into pieces. Or you can have plastic deformation. Here you can see a handle from a portable drilling machine, which then fell a couple of meters onto the ground, and the handle has got deformed, so it's no longer standing vertical, but it's got distorted over to the side. Now you can see that hasn't actually broken the handle, so as an engineer you can think of that as being a reasonably good result. There's then one more reason why things become unwanted, why they become useless, why people throw them away. And this, if you like, is the outlier. It's different from all the rest because it doesn't involve the product actually breaking or becoming less good at functioning. This is an example of obsolescence. This round computer mouse dates from the late 1980s. It was made by Digital Equipment Corporation and has a plug on it that now matches nothing else in the whole world. So although it still probably works, it's useless. And sometimes it can also be a trend. It doesn't necessarily mean that something no longer corresponds to regulations or is no longer correct for compatible with other equipment or software, that kind of thing. It can also be something like typewriters. I mean, there are hundreds of thousands of typewriters that still work that no one wants because hardly anyone wants to use the typewriter anymore. So this is also an important one to think about, obsolescence, and the idea that people then no longer want something because it's no longer useful even though it still works. I've just realized here that I've overlooked one last thing, buckling, when it comes to sudden damage. Now, you'll all know about column buckling. The idea is here that you have some elastic instability, and this means that at a certain load, a component will suddenly change shape and suddenly give way. Very often this then leads to some plastic deformation and permanent damage. Now, these failure mechanisms often happen in an interconnected succession. To give you some examples, if you think of an electric motor, like this one here is burnt out because the pump it was attached to seized, probably because the pump was blocked with sand or it was corroded, this kind of thing. And you can see here that the windings have turned black because the lacquer, the polymer insulation on the wire has got too hot to reach maybe 200, 300 centigrade. It's more than the wire can cope with, more than the lacquer can cope with without charring, and is then started to conduct some electricity. The electricity has then found a new path, a short circuit, and it doesn't flow through the coils in the correct way. The motor then no longer develops a torque and overheats. Now, coming back to the idea of a succession of problems as a failure mechanism, what could happen in an electric motor is you could have bearings that are lubricated with oil. If the oil seal then fails, it lets the oil out into the electric motor, which might not damage the windings immediately, but then very often attracts dust. If it's a motor that has an airflow through it, this one doesn't. This one has the airflow over the surface. And the dust will then form a layer of gum over the surface, which is a good thermal insulator, and that will cause the motor to overheat under a normal load. Another example would be a wind pump. Now, in lots of places in Africa, and I think also the big open farming areas of the USA, it's quite common to use a small wind turbine to drive a pump under the ground to irrigate a farm. And these have some kind of gearbox on the top of the column, and these are usually a very simple gearbox, and they don't have fancy oil seals or anything. What they tend to do is have some mechanism which splashes the oil over the gears or lifts up the oil and allows it to trickle back over the gears, and inside they have little deflector plates which then brings the oil back into the sump and keeps it away from the joints in the case. Now, if someone takes out those deflector plates, which are just small pieces of sheet metal, then very slowly, over the course of years, the oil is lost, and then the pump fails by wear. Now, there are very many other failure mechanisms. These are the big five of destruction. I can give you one or two more examples here that you can think about. This one here shows the perishing of rubber tires on an office chair. You can see these plastic wheels on the office chair caster originally had these little rubber tires. Over time the rubber perished, so it developed crosslinks between the polymer chains, it lost its resilience and its elasticity, and it cracked and fell off. If you're interested in failures of rubber, look at the Challenger Space Shuttle disaster from 1986. That was a loss of the resilience of the rubber O-rings caused by low temperatures. And one last one here. This is a chuck from a computer-controlled milling machine. And unfortunately, this is completely useless because the milling cutter got broken off inside. And you can see in the end there, there's the remains of a shaft, but it's well and truly seized in there, and the manufacturer didn't think to provide a hole where you could put a punch or a rod in there and hammer it out. And this has then been thrown away, despite the fact that it costs perhaps 250 euros, because it's impossible to get the broken milling cutter out of the chuck. So, what I'd like you to do for your assignment this week, I'll upload a list telling you who your partner is, and I want you to take their concept, or if they've got several, take one of their concepts and give them some feedback suggesting how it might fail. Which of these failure mechanisms could take place, which one is most likely, and perhaps how they could improve the design, or what details they should be looking at in the later design to avoid failures and maximize the product lifetime. I will say So far, I'm very impressed with the concepts that you've submitted, your first ideas. One I particularly like is the idea for sand-cast plastic shoe soles made using recycled plastic. I believe that was Garrett's idea. So there's some very good ideas in there. That's one I particularly like. If you've got any questions, don't hesitate to contact me. That's your assignment, and I'll see you next week. Thank you.